Good day, viewers, welcome back to my channel. Today we have the following interesting question. I to the power of I equals that. Here I equals square root of -1. If you have not subscribed to my channel, please subscribe, turn on the notification bell so that you'll be notified anytime we upload new videos. Thank you. Here I will be presenting two different methods of solving this problem. The question here is I to the power of I. Is it going to be real or complex? Okay, we don't know yet because I here is an imaginary unit. Okay, now my first method is going to be awesome. Okay, now my first method. Okay, according to Euler, the most beautiful equation in mathematics, e raised to I pi is equal to -1. Okay, now I'm going to take the root of both sides, so I have here square root of e raised to I pi is equal to, here square root of -1. Okay, now let us observe the property that the square root of a raised to b is the same as a raised to b all over 2. Okay, so here I have e raised to I pi all over 2 is equal to here square root of -1, which is iota here, so I have here I. Okay, now I'm going to raise both sides to the power of I. Okay, so here I have in brackets raised to I, and here in bracket raised to I. Okay, nothing will change if I make the right hand side to become left hand side, or making left hand side to become right hand side. So the right hand side I'm going to write this form, so I have I raised to I is equal to, in bracket e raised to I pi all over 2 close bracket raised to I. Okay, now I'm going to make use of the following property, that a raised to b in bracket raised to c is the same as a raised to b times c. Okay, now I have here I raised to I is equal to, e raised to I pi all over 2 times I. Okay, let me put it over 1. So I have here e. Now recall that I times I is equal to I squared, and this is equal to -1. Okay, so here I have first pi over 2, then in brackets I times I. Okay, so simplifying this, I got e raised to -pi all over 2. Okay, wow, that makes sense. So I say that I raised to I is equal to e raised to -pi all over 2, and this is a real number. Wow, this is interesting. So let's go to the second method. Okay, now I'll be writing this in polar form. Okay, so how do I do this? Let us recall that if we have z equals a plus ib, okay, where a is real part of the complex number and b is the imaginary part of this complex number, then our z in polar form can be written as, in exponential form, and not in polar form. Okay, so we have r e raised to I theta. Okay, so I actually mean in exponential form. Okay, so here let us say that our z is equal to I raised to I, and this I raised to I can be rewritten as 0 plus I in bracket then raised to I. So maintaining a real part, which is 0, an imaginary part here, which is 1. Okay, so we're going to find the modulus of z. Okay, our modulus here is equal to, r, and that is equal to square root of a squared, which is 0 squared, plus b squared, which is 1 squared. This is equal to square root of 1, and this is equal to 1. Okay, here our argument theta. Our argument theta is given by the formula, the tan inverse of b all over a. So here, remember, b is the imaginary part and a is the real part. So this is equal to the tan inverse of, the imaginary part here is 1 all over 0. So, 1 all over 0 is approaching infinity. So, and we know that the tan inverse of infinity in radians, so we have it as pi all over 2. Okay, so we're going to write our expression here as follows: z is equal to I raised to I, which is equal to here we have r. Our r is 1 times our e, then raised to I, and again our theta here. Remember, this is in bracket. Okay, then our theta here is pi all over 2, close bracket, then raised to I. Okay, so we get from here e raised to pi over 2, then I times I, and this is equal to e raised to negative pi all over 2. Thank you for viewing, and please make sure you subscribe to our YouTube channel for more interesting videos.